you all hear me? I know you really can't talk, but if you can just like private message me that you can hear me, we can start. Okay then. So first I want to go over some of the logistics of this class. This will be, I believe, a 9-week course, and we'll cover some topics that I feel are important for the AMC 10, and these things can also be used for other competitions, not just AMC, as these are generally universal concepts. As for the problems, none of these are for homework. In fact, there is no required homework for this course. However, if you guys want, I can post extra problems after class that you guys can do, and then I can post solutions to those as well. Yeah, that's about it. Does anyone have like any questions? Just private message me questions, I can answer them for a little bit. If not, this isn't based off of a book or anything, so I really can't assign any chapters, but I can always just find more problems for you guys to do, and then I can just solve them for you as well, so that if you want to look for a problem, you can. Anyway, if no one has any questions, I'll just get started. And so today's topic is going to be about circles, which in itself they seem like very simple things. Okay, well, is the volume good right now, or sorry? Can everyone hear me clearly? Well, that can be sort of a problem, but I'm not quite sure how I can adjust the volume of my mic or anything like that. But I'm on a laptop. I'll try to speak as loud as I have an external mic, but okay. Anyway, I'll just try to speak as loud as I can, and yeah, that's probably the best I can do. Okay, and just for info, I am currently using a laptop that is upside down, which is why if I am writing on the whiteboard, I might cover my video with my hand, just so it doesn't look weird. Anyway, let's start. Circles by themselves, they seem like very simple things, as they're just a set of points that are equidistant from another point in a plane. However, when using like problems, they can be used in many different ways. So we'll start from what I think are the basics. First, I'm sure you guys all know the area and circumference of a circle are pi r squared and 2 pi r, where r is the radius and pi is just a constant, 3.14, whatever. But that's usually not relevant. And we can calculate, or we can call a sector of a circle basically just a portion of the circle, as you can see in this diagram right here, that it's just you connect the center to 2 points on a circle, and then just like the slice that you take out of it is the sector, and then we can define this angle or the central angle as just like the angle basically. And on a unit circle, which is basically when the radius is 1, this angle is equal to the arc length in radians, where we have normally we have 360 degrees in a circle, but in radians this is equal to 2 pi radians. And that this is, sometimes you'll see problems solved between degrees and radians, but just so you know that that's how you calculate them. Okay, give me a minute. As you see here, the area of a sector we can just calculate as just a fraction of the area of the circle, and the fraction can be determined by the ratio of the angle of the central angle to 360 degrees or 2 pi radians. The first theorem we want to talk about is to the person who has private messaged me, I'll try to address that after the class is over. But there's really nothing that can be done right now. So anyway, the two-tangent theorem basically just states that if we have any circle and we have any point, we can always draw two tangent lines from that point. Well, the point has to be outside the circle, obviously, but we can always draw two tangent lines from the point to the circle, and these lines are always equal in length. And we can actually show this by letting the center be O and then just connecting the center to the two points of tangencies. And since the radius and the tangent line are always perpendicular when it comes to circles, then we have two congruent triangles, AOC and AOB. So we can use that to show that these two lines are the same. And then whenever we have a geometry problem like that, you should always look for these two tangent lines and connecting the center to an extra point, so that we'll have like an isosceles triangle if you can make one. The next thing I want to talk about is when we have two tangent circles tangent to each other. You can always, pro tip, connect the two centers, and then it will pass through the point of tangency, and this tangent line will be perpendicular to this line as well. And one way you can think about this is that the radii of each of these circles are tangent to this line. Can you guys see my mouse? I'm not sure. But the radii are each tangent to, not tangent, are each perpendicular to this line, and they both intersect that line at the same point. So the two radii must be on the same line. And again, this trick is you usually don't have to prove it. It's just generally taken for granted when you solve geometry problems involving tangent circles, which are really quite common. So now, a big aspect of circle problems in the AMCs is finding unusual areas, or areas of just sort of weird shapes that don't have a defined rigid formula for. And a very common one, or very common part of these areas, is just what I call a circular segment. And that's really just the area of a sector minus the area of this triangle. So you can just think of it as you find the area of the sector based on the ratio of this angle to the ratio of this whole circle. So then you can find the area of the sector. And then you find the area of the triangle. And you can do that. Usually they give you a good angle for here. And then you can just find the area of the triangle in whatever way is fit for that situation, and then you subtract. And then another thing I want to talk about is inscribed angle theorem, which basically says that for any arc that we have that is defined by just two points, here and here, any point that we pick on the circle, let's say we pick here and connect it to these 2 points, this angle is always going to be equal to half of the central angle of this arc, and it's also going to be equal to all other possible angles formed by the points, as you can see by the diagram. In addition, this green angle, which generally isn't too important to consider, but is also equal to the inscribed angle because it is supplementary to this angle right here, and this angle is just half of this angle is a supplement of an inscribed angle because the two angles together, they represent half of this arc and half of the large arc. Again, not something that you really need to concern yourself with, but it's interesting to know. And another interesting part is, Anyway, another interesting thing to note is that this inscribed angle theorem also works to a certain extent with tangent lines. So if this line right here, let's call this AB, is tangent to the circle O at this point B, and we have any other point C, can be anywhere in the circle, does not have to be there. Then we have the angle of this BDC is always going to be equal to angle ABC if AB is tangent to the circle. And this is actually not that hard to show because we can just use the fact that this angle is just going to be twice of the inscribed angle, and BOC is isosceles, so that we have that this angle plus this angle is equal to 90. So then after you do a little bit of angle chasing, you'll find that they're equal. You can check this later if you want. Now we'll talk about the relationship sort of between circles and triangles. For any arbitrary triangle, let's say that the length of the sides are A, B, and C. Here the circumradius of the triangle, which is basically this, if you draw a circle around the triangle such that all three of the points A, B, and C are on the circle, and there's actually only one unique circle that will fit this property, which I'm not sure how to prove right now, but anyway, then you know the radius of the circle is just equal to the product of the side lengths. If the side lengths are A, B, and C, it's just equal to the product of the side lengths divided by 4 times the area. And often you just have to remember this formula, and questions that are asking about circumradius become really easy. And anyway, and then the in radius of a triangle is basically the radius of the circle that we inscribe the triangle. No, it's the radius of the circle that we inscribe inside the triangle. So if we have like a circle, so here's a circle, and then we have a triangle like that, right? Then this is actually a really bad drawing. Let me redraw it. Please stop annotating things. Anyway, let's say we have a triangle. There's only one circle that can be drawn so that it's tangent to each side of the triangle, and the radius of this circle is the in radius. And then we claim that the length of this radius is going to be twice the area of the triangle over the perimeter. And we can show this by just connecting the center to the 3 vertices. And then if we let this be R, and R, and the perimeter is just the sum of the 3 side lengths, A, B, and C. This 2 times the area over the perimeter thing, what this is basically saying is that if we just cross multiply here, we have twice the area is equal to the radius times the perimeter. And this is equal to the radius times A plus the radius times B times the radius times C. And we know that the radius times A is just twice the area of this triangle because base times height is twice the area of a triangle. So then we can just apply this to each of the triangles, and then we'll just get twice of the area. And that's how you show that. And a special case for the in radius is when we have a right triangle, in which case the in radius can still be found using this area, but it's often easier just to use the fact that it's a right angle right here. So then we have that this in radius is just equal to this length right here. And this would actually just be A plus B minus C all over 2, which we can actually show using the 2 tangents theorem. Like if we let this length be x, this length be x, the radii are also x. And if we let this length be y and this length be z, then this length is also z, and this length is this length is also y. So then A plus B minus C is just x plus y plus x plus z minus y minus z over 2, and that's just x. So that's something you can keep in mind. We're not done to the problems yet. And this one last concept with circles is probably considered to be the most advanced part of it, and we call it power of a point, and we call it power of a point because these ideas all refer to how a circle can interact with a single point. So this is circle 1, this is circle 2, this is circle 3. I'm not sure who's annotating, it's sort of weird, or it's just glitching, but if anyone is annotating, it'd be nice if you didn't. Okay. For circle 1, we have that AE times EC is equal to DE times EB, right? And circle 2, we have AB squared equals to AB squared equals to BC times BD. And for circle 3, we have CB times CA equals to CD times CE. And now all of these can be shown using similar triangles and inscribed angles. And I'll show you the first two, and I want to see if you can try a third one on your own. Basically, for the first one, we have vertical angles here are equal, and then angles CDB and CAB are both inscribed angles to the arc CB. So we have by AA similarity, EDC and EAB are similar triangles. So from similar triangles, we get that DE over AE is just equal to CE over BE, and then cross multiplying gets our exact result. For circle 2, we just connect AC and AD like so, and then you realize that since AB is tangent, we have that this angle is equal to the inscribed angle right here, and then from there they both share triangle ABC and triangle DBA both share angle B, and their angle D and A are the same. They're similar as well. Okay, so basically, okay, so some of you probably didn't really understand what I just said, so I'll just try to I'll try to clarify a little bit. Okay, so the purpose of power of a point is basically saying that we know that we have a circle. We know that we have a circle, and we know that we have a point. It can be inside the circle or outside the circle. Doesn't matter too much. For the first case, we have that for any point inside the circle, we can draw any two chords that intersect at that point, and if we label them like so, the products AE and EC will equal to the product BE and ED, and this can be shown using similar triangles and inscribed angles, as I have shown that these are vertical angles, and just angle CBD and angle CAD both face this arc right here. So these angles are also the same. So once we have that, then we can just use the ratio of the side lengths from similar triangles to find this. And in case any of you are wondering what similar triangles are, they're basically just two triangles. They can be congruent, but they don't have to be, that have the exact same angle measurements. So that like this angle equals this angle the same as this angle, and so on. And this also means that their side lengths are in proportion with each other and themselves, meaning that the ratios between any two side lengths will always be the same as long as they're corresponding with each other. And the ratios between any two side lengths of the same triangle are equal to the ratios of the corresponding side lengths of the similar triangle as well. So, and that's a very powerful tool that we'll probably talk about next week a little bit more. But anyways, we can basically show each of these three statements are in fact correct. And for any of you working on the third statement, there are multiple ways you can do it. The first way is just realizing that if we take the second circle, we already know that this statement is true, and let's say we draw a tangent right here. and pretend that's tangent because it's better that way. Then we know that BC times AC is just the same as CF squared. We know that CD times CE is also equal to CF squared. So then by the transitive property, they are both the same. Of course, you can still use similar triangles. I believe we just connect the sides like this, then we have inscribed angles are the same here, and they share the same angle. So then we have triangle CAD and triangle CBE. But anyways, just if anything, you don't always have to remember how to prove it, but try to remember these. They're good for you, I promise. So those are what I feel like were just the basic ideas, but I want to give you some methods, as just knowing certain formulas isn't going to get you anywhere. You still have to be able to understand how to apply them and what to look for when you encounter a circle problem. And the number one tip I always have is whenever you have a problem with circles, always try to join points that are important, especially a center to any point of tangencies, or like if you have an inscribed circle, always try to connect the center to the vertices of the shape. And another one is that the Tagging Theorem, even though it applies to right triangles, it shows up really often in circle problems, especially where you can make a right triangle. And usually when a problem requires it, you'll have an unknown length or an unknown radius, and they're going to ask you to find the length of this side, and you can usually do this by expressing it in terms of the radius and also in terms of some kind of Pythagorean theorem. There are example problems later that will be demonstrating this. And another one is don't be afraid of variables. For example, making lots of variables for like a radius or a sine length. While they can seem confusing, it's often better to have something representing the value than not having anything and just staring at a blank diagram. And especially when it comes to the area problems, you want to try to dissect the diagram into something that can be easy to understand. And what I mean by that is to draw extra lines so that you can make the diagram itself, instead of just being one daunting shape, into just little shapes that you can find some combination of and turn them into, like, you probably can't see it because someone erased part of it, but if you I did post this handout on Classroom as a PDF, so if you can always look at that for reference. Anyway, where was it? So basically, if a question is asking you to find some weird area, like let's say we have like this actually is a problem, and then it's asking you to find this area, then you just know that you want to find the area of the semicircle and subtract this area of this sector, and then usually it'll give you a bit more information, like this is like a 60-degree angle or something. But generally speaking, just because you don't know how to find the area of the shape doesn't mean it's not possible to find the area of said shape. And this is especially for AMT10. It's fine if your diagram or if, unless they provide a diagram, it's okay if your diagram is not perfect, as long as you can sort of tell it's a circle and nothing is super messed up. It should serve its purpose. And this tip works for all the competitions where it's more speed-based than like something like the AIME where you have 3 hours for 15 problems. Then you can take your time and draw a good diagram. But don't stress too much if it does not look perfect. So anyway, I think we can start working on problems now, and just want to preface this by saying that we might not get to all the problems in this class, and if we don't, I will be posting more videos on Classroom of the solutions to the problems we did not get to. And these problems are not for homework. we will be mostly going through these in class. Actually, probably mentioned that in the beginning. But yeah, I just want to say again, these are not for homework. You can do them if you want. And the starred problems, some of them are starred at least, are what I consider to be the more important ones. So if you can't go through and understand all of them, at least understand the starred ones. Okay. So what time is it now? I can't see. But we'll start with this problem. This is, actually, I've labeled all the problems so you can get an idea of what kind of difficulty they were. And if you still need help with them, you can always look them up on AOPS, and they'll have a free solution for you to see. And these are all former AMC 10 problems that I removed the answer choices of, because answer choices aren't really helpful when you're trying to learn. Anyway, I think I can give you about like a minute or so. Just read through the problem and come up with ideas. And if you can solve it, that's great. Please private message me your ideas. I'll give you guys a minute, and then I'll present a solution, or at least a way to approach this problem. If you have any questions about anything, you can private chat. Okay, how do I remove the annotations? Give me a minute. Don't worry about it. I know what I'm doing, 100%. Yes, yes. Please give me more instructions. Okie dokie. I wonder if there's probably should be saying that prevents people from annotating. I'm not sure if their co-host has stopped it, but thanks for letting me know, I guess. Okay, yes, I have. Okay, I think it's been a minute. Anyway, so basically, all you need to know for this problem is that you're trying to find the area of the ring. The area of the ring is just you subtract the area of this big circle and of the small circle. And we know the radius of the big circle is just b, and the radius of the small circle is just c. So the area that we want to find is just b squared pi minus c squared pi. And this is the correct answer. You can write it in many ways, but you'll find if you actually found this problem in NC10 that the only answer choice that matches would be a squared pi, as you can just see from the Tagging Theorem. This is true. But yeah, if you got this answer, you are correct. Okay, next problem. Okie dokie. Okay, well, if you have seen this problem already, then I'm not sure what to say. You can start working on the next one, I guess. It's right here at the bottom. Yeah, if you've seen this one, just work on this one for now. This one would take a little bit longer to solve, I'd say. And I'll give you a little bit of time and then I'll start. Okay. If you don't understand anything, then can you please elaborate on what you don't understand? for someone private messaging me at least. Please elaborate. Okay. Internally tangent. Basically, all that's saying is that the circle is inside the other circle, like that. The center of the circle is within the other circle. Externally tangent, on the other, that's a terrible diagram. The externally tangent, on the other hand, is just the exact opposite, where the centers are not inside any of the other circles, like that. So yeah. Concentric just means that these circles share the same center. That's okay. The diagram doesn't show that, but basically these circles have the same center. That's concentric. Oh yeah, if you're still working on this previous problem, you can keep working on it. There's nothing wrong with taking more time to understand the problem. If you have more questions, just feel free to ask. Ooh, what is an X circle? I don't think this is in any of the questions, but basically an X circle is where you have, well, each triangle has 3 X circles. If you have a triangle here and we extend 2 of the side lengths, then the circle tangent to one of the side lengths and 2 of the extended side lengths, this is an X circle. And you can probably imagine there's an X circle on this side of the triangle, and there's another one on this side of the triangle as well. Which parts can you not see? Because my screen share is like everything's on my screen, so it's hard to tell. Okay, if you can't see the drawing of the X circle, it's, oh, well, not like that. It's like that. Okay, anyway, I think it's time that I can share the solution to this one. I've already seen a few correct answers from some of you. But basically, we first draw a decent diagram. Does not have to be really good, but it still has to work. Not like that though. That's not very good. And then we have three circles of radius 1, and they're each externally tangent to each other. So that means we're going to have something that looks like this, right? And we know that each of these lines will pass through the tangent points and the other circles, and this is just one point, pretend that it is. And this, okay? So we know that the circle has radius 1, or these small circles have radius 1, and we want to know what the length of this big circle is. Again, since we know that the line between the 2 centers of a circle, this actually applies if it's internally tangent or externally tangent. This line will still go through a tangent point. So we have the center of the circle is, or the radius of the center of the circle to the tangent point will pass through the center. So let this length be r, right? This length. Then we have r plus 1 is going to be the value that we want to find. And again, this triangle that we've made, it's upside down, but the triangle that we have made with the 3 centers as the vertices, like that, it's an equilateral triangle, and each side is just 2 as 1 plus 1, right? You guys can't answer me, so I'm talking to myself. So basically what we end up trying to find is just this length right here. And since this is an equilateral triangle, we actually know that, or okay, this is where it gets a little bit sketchy. But take my word for it, it's an equilateral triangle. Everything in this diagram is symmetric. This means that this point is going to be, you can call it the center of the circle, not circle, the center of the equilateral triangle. And it just so happens that since it's an equilateral triangle, basically every single special point is going to be this one point. So that being said, this means that this length that we try to find is just going to pass through the centroid of the equilateral triangle. Yes, you raise your hand. I don't know if I can unmute you or not, but you can still ask me a question. But either way, there are a lot of ways to think about this, but I think the easiest way to think about it is that since this is an equilateral triangle, the special point is going to be literally every single special point you'll see in a triangle. I mean, this is the circumcenter. It's going to be the incenter. It's also going to be the orthocenter. It's going to be the centroid, and etc. But so we can say the special property of this point, this point in the equilateral triangle, just call it the center of the triangle because it's basically it's the center. Okay. Basically, a special property is that if we connect it like this, so we drop the height and then we connect it to another vertex. You know that this is symmetric. So this is 30 degrees and this is 30 degrees like that. So this triangle is going to be 30, 60, 90 triangle with this length being 1. And then simply put, we can find using the Tagging Theorem length of the total height. This total height is just going to be the square root of 3 over 2 from the Tagging Theorem as seen. And then we also know that since this is a centroid, okay, actually I should take a different approach to this. Let's just, I know that this is probably not the best time to be going over this, but for any triangle, we would call this point the centroid if it's the intersection of the medians, and this point will divide each median into a ratio of 2 to 1. And for an equilateral triangle, the medians are just the heights. So we know that if we go back to our example, this was 2, this was 1, this was square root 3 over 2, which means that our desired length is just 2/3 of that, which is square root 3 over 3. Now what all this means is that the radius of the large circle is just r plus 1, right? And r, this length, is just square root 3 over 3. Wait, no, it's 2/3 of it. Yeah, okay. So it's just like that. Did I do something wrong? I did do something wrong. I did not scale it. So this is actually, I really need. Okay, as I was saying before I made a mistake, this is, the length we're looking for is 2/3 of the height. This height is actually the square root of 3 because 1, 2, root 3. And then our desired length is just 2 square root of 3 over 3. And then 1 plus 2 square root of 3 over 3 is the answer. You can also write this as 3 plus 2 square root of 3 over 3. If there are any questions, you can ask them. I know that my explanation may have been a bit roundabout. Anyway, moving on. Spot's doghouse. This is an area problem. So all right. So question, what is an incenter, circumcenter, and orthocenter? I can probably explain more in the triangle section, but basically, I've already mentioned that an incenter and the circumcenter here, they're just the centers of the incircles and circumcircles, where, like, for example, the circumradius is just from the circumcenter, and the inradius is just from the incenter, if you know what I'm saying. And the circumcircle is just the circle where you inscribe the triangle into. The incircle is just a circle you inscribe inside of the triangle. An orthocenter is just the intersection of the altitudes or the heights to each base of a triangle. that point itself is really not that special, to be completely honest. It's just that an equal triangle point, and that makes everything easier. Anyway, I think that this is probably a bit poor judgment by me, but we're sort of running out of time. Actually, anyway, so I'll just go over this problem a bit faster. We know that this Spot's doghouse is a hexagon, right? Let's just say that this is the point that the rope is tethered to. Each side length is 1, and we know the rope can go 2 units in each direction like that, right? This class is supposed to be an hour long, but I'm technically free to drag this on however long I want. However, there are probably some people here who can't stay for that long, so that's why I'd like to try to at least like give a glimpse and commentary about everything, because it'd be sort of unfair for people for me to drag this class longer than it's advertised as. But anyway, we know that Spot can only go to a point 2 yards away at most. So what this problem seems a lot like is it's just like saying, oh, what's the area of the points that are within 2 yards of this point? And that's exactly like what a circle's definition is. There's a set of points in an exact distance away from another point. And since we know that it's asking for the region that he can reach, it's referring to the area inside of this circle. Yes, you're right. It actually is a sector. It's actually multiple sectors, but I like to call it a circle because honestly, it's easier. But here we have a problem. He runs into the side of the barn or whatever it's called, doghouse, right? So he can't just like go. His rope can't go through this side. It can only just wrap around like that. So what ends up happening is that we have these 2 sectors of radius 2. We also have these 2 smaller sectors of only radius 1. So if you can dissect the problem like this, it becomes just finding the area of a few different sectors. You'll notice that this is symmetric, so you really have to find the area of 2 sectors. For example, we know that this angle is 120 degrees because of the hexagon. I'll probably go into that more later, next class. But let's just say that it's a hexagon, so this angle is 120 degrees, right? That means that the rest of this angle is 240 degrees, and again, since it's 120 and it's a regular hexagon as stated, then this angle would be 60, and the same here. Now, to find the area of the region, all we have to do is take the area of a sector. 240 over 360 is a ratio of the central angle to a full circle, then times what the area of that circle would be, which would be 2 squared times pi. And then we add these 2 sectors, which are each 60 degrees, and the area of their circle is just 1 squared pi, right? And then if we just expand this, what we'll get is that the area of this is just 2/3 times 4 pi plus 1/3 pi, as 2 times 1/6 is 1/3. And then this is just going to be equal to 3 pi. And that is their answer. So if any of you got that, congratulations. Now, it's sort of unfortunate that I can't get through everything, so I'm just going, so here's what's going to happen. I'm going to skip over the problems that don't have stars, and those are the problems that you guys can look at after your class, or if I have more time, I'll go back to them. But just focus on the starred ones for now. So this one is a lot of words. The number of inches in the perimeter of an equilateral triangle equals the number of square inches in the area of the circumscribed circle. What is the radius in inches of the circle? When you see a geometry problem with a lot of words, first thing you should do is either you draw a diagram or you just draw a diagram. That's what you should do. So we basically have an equilateral triangle, meaning all sides are the same. And we also have the circumscribed circle, which is like the circle around it, okay? And we know that the number of inches in the perimeter, if we let this be the side length, 3s, is equal to the number of inches in the area of this circumscribed circle, which we'll just call A, right? And this is an equilateral triangle, as I mentioned this earlier. The circumradius is just going to be, the circumradius is just going to be 2/3 of the height. Or in this case, you can actually just, if you know how to find the area of an equilateral triangle, you can use the circumradius formula. But either way, this length is going to be s√3/3. I'll let you guys verify this later, but this is going to be the radius of the circumradius of this triangle. Then from there, all you have to do is apply the area of a circle formula, which is just you square this. So you have s²/3 as √3/3 squared is 1/3, and then you multiply by pi. That's area of the circle, and this equals to 3s. So we know that pi s equals to 9, and s equals to 9/pi. Is this our final answer? I'll let you guys just think about that for a second. And yes, some of you have, I can't call on you because I can't unmute you. But basically, no, this is not our answer. We're asking for the radius of the circle and not for the side length of the triangle. So to find the area, we just multiply this by, this is the radius. We multiply this by the square root of 3/3. So our final answer, and the correct answer, is actually 3√3/pi. So again, with the linguistics questions, please don't get caught in traps. They're purposely written like that. Oh, I can unmute people. That's nice. I should probably figure that out later. Actually, no. Okay. Okie dokie. I'll try to unmute some people so that they can answer for this next problem, because that's a slightly harder problem. Okay. So I'll let you guys read this problem by yourself, and if you have any ideas of what to do, please just private message me, or actually just I can have the host unmute you if you have your hand raised. So if you can do that, that'd be great. And yeah, if people stop annotating, that'd be great too. Honestly, it's not too big of a deal if it's just on the side. I mean, as long as it doesn't completely interfere with what I'm trying to do, I'll tolerate it for now. Okay, I see. Skylar, you seem to have an idea. What do you say?
Okay, so this is like another circle over here, another imaginary circle that has here. This is the center, and then I go and draw a line from here and to here, and then I figure out that this small area over here plus this the exact same area as this small area over here plus the triangle, and the small area is basically like a part of the circle, the semicircle, minus the triangle.
So let me try to figure out what you're saying. Are you trying to, if we connect these, do you want to connect these?
Connect it like in a more circly way.
you want to connect it in an arc like that.
Yes.
Okay, and then you're saying that you can find, if you connect this, you can find the area of each of these sectors or something like that.
Yeah, each of those thingies.
Yes, that's true. You can find the area, but the problem with what you're saying is that now you're going to be left with this weird area right here. I'll draw it out. It'll look like this. Okay, and you certainly can find the area of this, but it's definitely not the easiest way to.
No, like what I mean is
That's
like I add up this circle, this circle, this circle, subtracted by this, and then add those two areas over there. So like I just go and remove the repeated area.
Okay, so you basically you add these semicircles, and then you subtract their overlapping areas.
Yes.
That can work actually. Let's try that. So okay, let's make this a bit easier. Oh, everything's annotated right now. Shoot. Okay, so what Skylar is suggesting is that we can just consider this semicircle like this, another semicircle like that. Then we can express this white area as I think the best idea to find the area of the shade region is just find area of the big semicircle, then subtract whatever this white unshaded area is, as it seems more likely to be able to find this area than the other area directly. So one way you can do this is just if we can add the areas of each of these three semicircles, and we know that they're all of radius 1, and therefore each area is just going to be pi over 2. So we know the total area of the white area is 3 pi over 2, but we have to subtract how much each of these sections is overlapping. Now each time we add two semicircles, or add one semicircle to this middle one, we'll be adding an extra, we'll just call these like A sections. They sort of look like A. We'll be adding an extra like A section, so to speak, to our area. You have to subtract them off so that they won't be counted multiple times and they won't give us incorrect results. Right? So anyway, yeah, don't annotate, please. Okay. So how are we going to go about finding such an area? It looks like that. And well, first just notice that this triangle itself is equilateral, and you can actually show this because each of these semicircles have radius 1, so all the sides are the same. Yes, the time. I'm not sure what time it is, but it's probably okay. Oh, it is. No, it's still some time. But either way, we can find the area of this by just finding the area of two sectors overlapping and subtracting away a triangle. Okay, please stop annotating. That'd be great. Yeah, I'll deal with this next class. We don't have too much time in this class. But okay, so we know it's equilateral, so each angle is just 60 degrees. Now, a 60-degree angle means that it's 1/6, that's 60 over 30. It's 1/6 of the area of the total of the big circle with the radius of 1, right? So in the area of this sector would be 1/6 pi. And we can just say that by symmetricity, the area of a sector like that is also 1/6 pi. And then now we just have to find the area of the, okay. They're actually, and then we can subtract the area of the triangle, and the area of a triangle is just going to be s squared root 3 over 4. I'll talk about it later, but we'll say it's true for now. So it's just going to be square root 3 over 4. And now this area is overcounted twice, I believe. Yes. So we have to subtract twice of this. And basically, if you do all that calculation and stuff, I don't have too much time, but actually, wait. But basically what happens is that, I'll let you guys finish this problem. I really have to go to another one. But basically what I'm saying is that eventually, if you calculate this out, you'll get that this region, or actually, I don't actually have the exact numbers, but eventually you'll get that their final answer is going to be the area of the semicircle, which is just pi, and then minus whatever. Okay, please. Okay, what would you like to say? If you have your hand raised.
Oh, I had a question real quick. So, for the when you guys were finding the overlap areas, after doing what Skylar did, like after subtracting those two semicircles, I'm confused how you found the areas. Like, did you inscribe a triangle, or I'm kind of confused.
Oh, okay, Skylar's referring to an area that looks like basically a triangle. Guys, can you stop annotating? And to these circle sections like that. If you look from the divisional diagram, they're basically just cutouts of this middle semicircle and a side semicircle. So where we have this sector is just from the left semicircle, and this one is from the central one. So we basically find the areas of each of these sectors, and then we subtract off the triangle in the middle. But either way, I'll let you guys finish this calculation. You'll get that the final answer is going to be the square root 3 over 4 minus pi over 24. And I'll leave you with that. I'll just first say that there actually is a different approach that you can take to this problem. If you connect the lines like this, right, then you can just simply say that you have these two 120-degree segments, right, or sectors right here, and then you have two equilateral triangles, and you have a 6-degree sector right there. Yeah. I'm probably not wrong here. If I am, I do apologize and try to see what I did wrong, but I really can't. Okay, this problem, I'll just tell you straight away, it's a number 22, but that does not mean it's impossible to do. Basically the idea behind this problem is that you can use a two-tangent theorem. And once you two-tangent theorem, and then plus Pythagorean, and that's basically it. Where you just let any of these lengths, if you can let it equal to x, you know this is 2 minus x. From two tangents, you know this is 2 minus x. This length is 2. This length is 2. So you know from two tangents, this line, if you call this f, so we know that CF is just 2 as well. So then we can use a Pythagorean theorem on CDE, and you can solve for x that way. And that is basically the idea behind this problem. Yeah, if you have to leave, that's fine. The recording of this class is going to be posted later, so anything you missed is going to be the answer to the last question. It's going to be the square root 3 over 4. Sure. Nope, actually, never mind. I chose the wrong. Yeah, you guys are right. I saw the wrong thing on my answer key. Don't worry about it. I am completely responsible person, 100%. It was actually yeah, 7 over 6 pi minus the square root 3 over 2. Yeah, it's my bad. But anyway, I'll just leave you with this. Generally speaking, knowing how to do the problem is honestly more important than being able to just crunch values. But if you want to actually crunch the values of this, you'll get x to just 2.5. Yes, this problem. This problem looks very similar to this problem right here. But the difference is that these three circles aren't all the same length. We have that circle A, it's not exact. It's very similar, but it's not exactly the same, as the calculations are a bit harder. We have circle A passes through the center of circle D and is larger than each of B and C. We don't know the radii of circle B and C, that's what we want to find, and we know the radius of circle A is just 1. So tip number 1, connect everything. It's for the better. Basically, what we can do here is that we know that the radius of circle D is just, the radius of D is just equal to 2, and that's because it's equal to the diameter of circle A. And yeah. So we know that this whole length right here is just equal to 2. We want to find this length R, and so all we have to do is express 2 in terms of R, and then we can solve. Yes, this is an isosceles triangle with sides of 1R, 1 plus R, 1 plus R, and 2R. And we have R is less than 1. So at first it may seem, well, okay, once you get to this point in a problem, it often helps just to take the triangle out of the diagram, as the diagram itself can look a bit cluttered and hard to think. Oh yeah, we also know that this line passes through the tangent point between the two circles because the diagram is symmetric. Basically, that's a way of saying that it looks like it's true, and so it's probably true. And if it wasn't true, then something must be wrong with math, because everything on both sides is the same, so it has to be going through the middle. That's how symmetry works, I guess. Okay, but either way, this is what our diagram should look like for now. So how do you guys plan to solve this problem? There's one method that you use for right triangles that's very helpful here. And yeah, it's the Pythagorean theorem. And first, it's not. Right, well, first off, angle bisectors only work if you have an angle bisector. This is not necessarily bisecting the angle. The correct response was the Pythagorean theorem, as you need right triangles and you have right triangles. You have to do the Pythagorean theorem twice, as we don't know this length, so that's an unknown, and we also don't know R. So we have that R squared plus X squared is equal to 2 minus R squared. But we also have that 1 plus X squared plus R squared is equal to 1 plus R squared. And basically, I can just expand this out real quick. R squared plus X squared equals to R squared minus 4R plus 4. And this would just be X squared is equal to 4 minus 4R. So then X would just then be equal to 2 square root of 1 minus R. And then we can plug this into this, we can substitute X in for the second equation. And after a bit of algebra, you have that 1 plus 4 minus 4R plus 4 square root of 1 minus R is equal to plus R squared. I'm all over the place right now. Plus R squared is equal to 1 plus R squared. And I wrote that in the wrong way too. R squared plus 2R plus 1. Then after some simplification, we can directly substitute for X squared plus R squared. That's an interesting idea, but the problem is when we expand this, we'll have a just an x to the 1 term that you wouldn't have accounted for, because when you expand the binomial squared, you're going to have 3 terms. So your idea is not going to work in this case. Anyway, so now we basically have one equation in terms of r, and if we move all the r terms to one side and just isolate the square root, you'll basically just get 4 square root of 1 minus r is equal to 6r. I think it's minus 4. And then you have the square again. And then definitely missed some. Yes, and then you can because 16 cancels out, and then you just have this equation right here. And then this is basically just a quadratic, except for you can factor in r. Is r times 36r minus 32. So we have r equals to 8/9 as r equals 8/9 as our answer. But this is just algebra bashing. It's not too important. What you really have to, what I really want you to take away from this problem is that be creative. Connect some lines, connect some points, and then try to see where you can express this same value twice. And then once you do that, everything just becomes a lot easier to manage, as you can turn just some random circles into a more friendly kind of problem, and then you can just bash out the rest, and that's about it. Okay, okie dokie, let's get this problem. Next problem. This is actually going to be, I think, the last problem, as our only other problem is the challenge problem. I'll leave this one open for now. This is actually a very recent problem, and if any of you want to try it by yourself, you guys can when you're free. You can either look up the solution, and I'll also post a pretty simple solution to this problem as well. But yeah, we won't be covering this today. But anyway, last problem for this class is in triangle ABC. AB is 86, AC is 97, and the circle that intersects with center A and radius AB intersects the line segment BC at points B and X, and we know that the lengths are integers. So what is BC? The first thing you should always do when you have a word problem and its geometry is draw the diagram. And in this case, we can just draw any kind of triangle. Usually that works. We have AB is 86 and AC is 97. So we know that the circle with center A and radius AB, it'll look like this part it'll intersect like here. So the plane is 86, and we have X like that, and this you can draw the rest of the circle as well. It's actually a sort of mandatory for this problem. Okay. So now we're given that BX and CX. Okay, wait, I did this wrong. Oh wait, we're talking about the wrong way. Sorry. I'm wasting your time here. I didn't interpret the problem right. But basically, let's try this again. Triangle AB, C. AB is 86. AC is 97. The circle with center A and radius AB intersects BC. Okay, that doesn't. Oh, no, it does. Okay. Intersects BC at points B and X. So basically, what they're saying is that the circle is going to be like, it's going to intersect here, then like intersect here again, like that. It's not tangent, so it can do that. And this is X. Basically, what we want to find is what BC is. Something seems wrong. You know, something seems terribly wrong here. And that was definitely not what I planned. Wait, no, everything's fine. I am totally not trolling right now. Okay, we label this point y, and now there really aren't that many great options to approach this problem when you think about it. You don't have much information, but there is one thing that we talked about in this class, earlier in this class, that is basically just imprinted onto the problem. Can you guys think of what I'm talking about here? That one method that's just pops out, so to speak. Yes, for those of you who have messaged me, you are right. It's power of a point. And obviously there's only one point that really has power here, and that would be C. And this is also where the fact that we know these integers comes in, because now we can utilize prime factorizations and stuff. So basically what we have here is that Cx times Cb is equal to Cy times, let's say this point is D, CD. This right here is probably one of the biggest mistakes that you'll see. Instead of doing CD, they'll just do CA. Many people do CA instead because there's no convenient point that is just on the opposite side of the circle. Make sure that when PowerPoint, all of these points are on the circle except for the point that you're taking the power of. So big mistake to take A. It's actually D that you want. We know that A is the center, so dy is actually the diameter, which means that dA is just, this is 86 like that, and this is 11. So basically, all you have to do is plug in numbers for this. Cx times Cb, we don't know yet, equals Cy, 11 times Cd, which is just is 183. Although, yeah, 183. Right? And 183 times 11, that's just 3 times 11 times 61. And yeah. And here, all we have to do is notice that they have integer lengths, which means that we know CB is greater than CX, and their product has to be equal to this. And so how do we know that CX isn't just 3 and CB isn't just 11 times 61? Or how do we know that CX isn't 11 and CB isn't just 183? Why is this not the case? Again, yes, I know I haven't talked about this in circle class, but basically we can use a triangle inequality, which basically means that side lengths of a triangle all have to satisfy something. That if their side lengths are A, B, and C, you must have that the sum of any two side lengths is greater than the sum of the third. Because if you think about it, the shortest distance between any 2 points in a plane is just a straight line. Any kind of like excessive path like A plus B, that's going to be longer than C. So if any of the other scenarios I proposed were the case, then we'd have that this triangle ABC would not satisfy the triangle inequality, as AC is just 97 and BA is 86. So we know that BC cannot be greater than or equal to 183. Therefore, that takes out both of the cases I presented, which only leaves the one case that CX and CB are just 33 and 61. So our answer is 61. Yeah, I'll write that here. So we can just simply deduce that of 3, 11, 61. Only combination of prime factors that would work is CX equals to 33 and BC equals 61, and that is our answer. I'll make sure to no, whoever annotated that, you are not correct. The answer is 61 because if you notice, BC contains CX. So we're not adding CX to get BC. The 661 is just CB. That's another thing with PowerPoint. I'm running out of space here, but for PowerPoint, if we have a circle, right, and then a point here, always make sure that you're multiplying this times this. And if you're taking the full length of the segment, each segment should contain this point as it's the powerful point, so to speak. We're never going to be multiplying just these two segments together. That's wrong, and it'll get you the wrong answer, and that's not fun. So yeah, now that's cleared up, and we are sort of over time. I'm just going to make a few comments. Actually, I'm not. Actually, I am. I'm going to make a few comments. Like for this one, it is a number 25. It is definitely not on the difficulty of what number 25 would be today. And all you have to do is simply construct a way to find the area, and you'll be able to solve this problem. And for this one, some of you may have actually seen this problem when you were taking the AMC 10 like last year. There are many ways you can approach this problem, and don't feel bad if you can't actually figure out the easiest approach, as I didn't actually figure out the easiest approach. I had to take the longer way. But just know that there are multiple ways to solve this problem, and yeah, brute forcing the area of the white shape is not the way to go, I'll tell you that. But yeah, I think that's just about what I wanted to cover today. If you have any questions, you can ask them right now, and I'll be happy to answer any of them. But if no one has any questions, you guys can all leave. Class is dismissed, I guess. I'll post everything. I'll post everything on either in YouTube or class. Either in YouTube or Classroom, I'll let you know. But yeah, you guys are no longer obligated to be here. No problem.